Art gallery problems. The original problem asks, given the floor plan of a gallery that's assumed to be a polygon, how many security guards are needed to watch over the entire gallery at once? Formally, if P is a polygon, we say that a set A dominates P if for every point of P there's a point of A, so that the line segment between those 2 points is contained entirely within P. The guard number of a polygon is the size of its smallest dominating set. So as an example, consider this polygon. Note that the red point can only be seen by the top yellow rectangle, and the blue point can only be seen by the bottom yellow rectangle. So we need at least 2 guards, one in each rectangle, since those rectangles don't overlap. 2 guards also suffices to monitor this polygon, because the red area can be seen by the red guard, the blue area can be seen by the blue guard, and the purple area can be seen by both of the guards. So the guard number of this polygon is 2. In the original problem, the interest was in finding the maximum guard number over all n-gons. This was found to be floor of n over 3. So what this means is that there exist polygons on n vertices which need floor of n over 3 guards to watch, and floor of n over 3 guards suffices to fully monitor any polygon on n vertices. So to see that there exist polygons requiring floor of n over 3 guards, observe that in this gallery there's no point that can see into more than one of the spikes. So you need at least 1 guard for each spike. You can also extend this example by adding more spikes. Every time you add another spike, it adds 3 edges to the gallery, and you'll need 1 more guard. To see that any polygon on n vertices can be guarded using at most floor of n over 3 guards, consider an arbitrary polygon and take some triangulation of that polygon. There's a result from graph theory that says the vertices of a triangulation of a polygon can be 3-colored. Fix such a coloring. Note some color class here contains at most floor of n over 3 vertices, because if all of them contained more than that many vertices, there would be more than n vertices in the polygon. So we take the color class that contains at most floor of n over 3 vertices and we place a guard at each one. In this case, yellow. So any triangle of the triangulation necessarily has a yellow vertex because it has one of each color. So since triangles are convex, every point of the polygon can be watched because any triangle has a yellow vertex that can watch over the entire triangle. It should be noted that all of this strategy shows that any polygon can be watched by at most floor of n over 3 guards. It doesn't necessarily give an optimal placement of the guards or the optimal number of guards. So for example, the guard number of this polygon is actually 2, even though coloring it with this triangulation gives you 3 guards. Since the original problem, several variants have been proposed. I want to briefly talk about 2 of them. The chromatic art gallery problem asks that we assign a color to each guard. We insist that if 2 guards can see the same point, we assign them 2 different colors. The chromatic guard number of a polygon is then the least number of colors needed across all configurations of guards that watch over the polygon. So that means that if you look at every possible way to position guards so that the polygon is completely watched, the chromatic guard number of the polygon is the fewest number of colors that would be needed over that entire set of guards. And note that this doesn't necessarily correspond to a minimal guarding set of the polygon. So note that if you take any guarding set of the polygon and you color each guard a different color, will satisfy the condition that 2 guards that see each other are different colors. So we can say that the chromatic guard number of any polygon is at most the guard number of that polygon. But we can often find improvements. So in this example, if we were to put a guard at the tip of each spike, And then no two guards in different spikes would share a point in their field, in their area that they can see. So we can color each of the guards in the spikes the same color. Then we just need to place one more guard along the spine so that it can see the areas that none of them can see. And this guard will have its visible area overlap them, but that just means that this last guard needs to be colored a different color. So the chromatic guard number of this polygon is 2, as compared to its guard number, which is 4. And it's also worth noting that this is a case where, even though the minimal guard number of this polygon is 4, we find the chromatic guard number using a configuration of 5 guards. So even though that we can often improve on the guard number to get the chromatic guard number, there do exist polygons whose guard number is equal to their chromatic guard number. So this bound can't be globally improved. The other art gallery problem I wanted to talk about involves replacing the guards with security cameras that are mounted at vertices. We also restrict the field of view of the cameras, so instead of being able to see all around them, they're limited to a cone that can only see in alpha radians. One question of interest here is, for what values of alpha is it always possible to fully watch over a polygon, assuming that you're limited to one security camera per vertex? It turns out that if alpha is less than pi, there exist polygons where you can't fully watch over the museum, even if you put a camera at each vertex. What about when alpha is at least pi? There is a tool from geometry that is useful in trying to answer this question. An ear in a polygon is a vertex V with neighbors U and W such that the line segment from U to W is contained within the polygon. So here is an example, just pointing out a vertex that is an ear because the line segment between its two neighbors is contained in P, and then a vertex that's not an ear. So Meister's theorem states that all polygons have at least 2 ears, and we can use that to show that when alpha is at least pi, every polygon can be watched by cameras mounted at the vertices. So to see this, we place a camera at an ear of pi, which exists by Meister's theorem. The ear and its neighbors form a triangle that's contained entirely within the polygon, and so since alpha is at least pi, this camera can see that entire triangle. So what we can do is then remove this triangle, think of it as an area that we've gotten for sure monitored by a camera, even though the camera can see points outside of the triangle. We remove this triangle, and we end up with a polygon with one fewer vertex. We apply Meister's theorem again to say that this polygon has an ear, so we can repeat this process by mounting a camera at that ear and then removing another edge or triangle from this polygon. And you continue this process until you just end up with a triangle. And at that point, once you mount a camera in the triangle at a vertex, you'll be able to watch the whole thing. So this decomposes an arbitrary polygon into a collection of triangles, each of which can be fully monitored by a single camera at one of its vertices. So it's important to recognize that the reason this doesn't extend to the case if alpha is less than pi is because if alpha is less than pi, you can make a triangle whose angle at the ear is between alpha and pi, and so mounting a camera at that angle wouldn't necessarily allow you to keep watch over the entire triangle. And that's the essence of the idea behind the fact that when alpha is less than pi, there are polygons that can't be watched, essentially because there will be points arbitrarily close to the camera that camera is unable to see.